Over 20 years ago, Dale Earnhardt and Bobby Labonte inadvertently changed the way motor oil is formulated today for your car. Hi, I'm Lake, the motor oil geek. Let's take a trip to Ohio to meet Mike Mucha and Bill Abraham, two of the men involved in the development of special oil for NASCAR engines that paved the way for today's API, SP, and SQ motor oils. So you might be wondering, why Ohio? What does Ohio have to do with motor oil? It's not like it's Pennsylvania or Texas or somewhere kind of famous for oil. Well, Ohio happens to be the headquarters of the Lubrizol Corporation, which they're the guys who invented zinc dialkyl-thiophosphate, zinc, ZDDP. So if you're going to get into the real details about high-performance oils, you got to go where the additives are made, and that's Ohio. So as promised, Mike Mucha, Bill Abraham. These are the guys that taught me the science of tribology, but you don't want to hear about that. What you want to hear is how racing oil has actually changed modern motor oil. And like I said at the very beginning, these guys were at the very beginning of this whole thing. Of course, you're only two of what I'm going to call the Fab Five, right? We need to give credit to the other three that aren't here: Doug Jane, John Martin, and Sarah Kipp. You guys, as a team, help us as a team, us being Joe Gibbs Racing, win a lot of races and a lot of championships. Where did it start, Mike? How did this whole thing begin?
Well, back in the late 90s, early mid-90s, most of the racing teams were using 2050 oils, something along those lines. More conventional oils, nothing specialized per se.
Oh, the Union 76, 2050 racing oil is what we all had in the garage for free, and everyone used it. Yeah. Well, that was for everywhere except Daytona, Talladega.
Right,
then you got fancy for plate races, and you use 5W30 Mobil 1.
Right.
That was the trick thin oil.
Sure.
Yeah, I remember one of the teams I worked at, we were sponsored by Kodiak and Levi Garrett, and we would trade cases of tobacco with the guys on the Penske team for drums of Mobil 1 so we could use that at Daytona and Talladega.
So that was a history in the mid-90s, pretty much conventional type motor oils, nothing really special designed specifically for racing. Richard Childress was working very closely with 76 on racing oils, and they were coming into a lot of failures on the track. And so that's where we got involved, because Lubrizol at the time was the supplier for additives for 76 lubricants. That's sort of the history behind where all this started. So the failures came into our offices, and we tried to help 76 out, and eventually became involved with both Richard Childress directly as well as 76 to provide some specialized motor oils developed specifically for them, not commercial oils, that they would use in the racing. And a lot of it centered around the plate racing. They really needed 1 or 2 horsepower more to really make a big difference. And so we got into the plate racing side of things and developed special oils for that as well. So it's 25, 30 years ago.
Yeah.
Things really started heating up in terms of specific oils for racing designed by the companies that designed the additives, not the oil manufacturers.
Before I met Mike and Bill and worked with the rest of the folks at Lubrizol, I knew nothing about motor oil. Now, I thought I knew about motor oil, but I didn't. Before that, everyone was just buying an oil that was supplied by the manufacturer. Now you're talking about really behind the scenes, the additive company designing an additive package specifically for the oil that would never be on the market.
Right.
Only made for the race team.
Right. I would call it boutique racing oil.
Right.
That's what we were developing.
And that began with the guys at Childress, camshaft wear issues and things like that. Somewhere along the way, and I know my version of the story, but I'll let y'all tell your side of the story, the guys at Joe Gibbs Racing got involved. And I think, Bill, you said it started with a phone call about piston rings.
Yeah, piston rings. Yeah, we were working. I was working specifically with an expert ring designer for actually HDD, heavy-duty diesel engines, Mac T9, solving that problem for industry. And that same person was working with Joe Gibbs Racing on a ring design issue about blow-by, where they were seeing too much deposits in the top part of the motor engine. But they were really having problems with the cam wear.
Yeah.
Early in the season, I believe NASCAR 2000 with Bobby Labonte and Tony Stewart. So they gave a call to me. I got a cold call probably a week after NASCAR's top race, the Daytona 500. And so we discussed the situation, and we said, well, we could solve that problem. You probably have this, and that problem. The balancing the detergent, probably too much dispersion. Again, using more of the conventional motor oil, and we could redesign this and have the right anti-wear enough, but not kill you for speed and for horsepower. So
We'll get back to that, by the way.
yes. So immediately I forgot the phone. I called Mike Mutual, who's over in the commercial side of things. I'm on the research side. Mike's in the commercial side of things. And so, hey, Mike, I just got a cold call from Joe Gibbs Racing. Needed this. You're gonna have to run this up the flagpole to see if we can do this, because the Richard Childress thing was about 4 years before that, but it really didn't take off into something on a more permanent basis. And so I'll leave it to Mike what happened. When I called you and told you everything, you said, well,
we just can't start working on motor oils for a racing team. That's not part of our business plan.
Right.
Yeah.
So at the time, James Hambrick was head of the engine oils division, who eventually became the president of Lubrizol. So I go in there. He's a Texan from Texas, and I explained the situation that Bill was telling me that Gibbs needed help with, and we never worked really with a race team directly. It's always through our oil company customers, right? That's the way things work.
You're providing a service to your
the
customer,
oil, right?
who is the oil company.
Who's then dealing with the racing team. Well, this was different because we're working, now we want to work directly with a racing team.
Right.
So I go into the office of James Hambrick and I explain the situation. I say, so boss, what do you think? Can we do this? And in his southern drawl, he goes, I'll give you enough rope to hang yourself. And I said, that's good enough for me. Let's do it.
So
that's what we did.
Mike called me back, and then we started having discussions with him mechanics at Joe Gibbs Racing.
Yeah.
So
Mark Cronquist
and Joe Hornick.
Yeah. So the other side of the story, that from Mark Cronquist's side, because I wasn't even involved in the team at that time, but what Mark told me was that from like 92, 93, somewhere early in the beginning of Joe Gibbs Racing, Shell had been one of the sponsors. Yes. So the Shell Global Solutions folks supplied Gibbs with an oil that was this racing oil, right? That wasn't commercially available, but and they were good. Right. So that lasted through 1998. In the 1999 season, they didn't have that special oil anymore. Oh. So now they're going back and they're just using whatever's commercially available. None of the commercially available oils could match the performance of the special Shell stuff. And in 99, Bobby actually suffered 2 engine failures, both flat tap and camshaft failures during races. Right. If you only limit that to 1, Bobby wins the championship in 99. So literally the oil problem cost Gibbs the championship in 1999. So when they go to Daytona in 2000, and during practice, not during the race, they lose another engine to flat tap it. It's like, we got to find an answer. So that's the other side of the story.
Wow, I didn't know that part.
Since this channel is about science, not speculation, I'd refer you to SAE paper 2000-01-3553, where Lubrizol, working with 76 and Richard Childress Racing, discovered how detergent and dispersant additives do compete against ZDP and friction modifiers, which directly affects engine wear. One of the authors of this paper is Doug Jane, who is one of my mentors in developing the products at Joe Gibbs Racing. But what happened after that? Because I think the development angle here goes very different. Like you said, with the Childress deal, it was pretty much down to the change in the detergent package that 76 was using that's what caused the cam problems. You want to kind of go into that? Because it was a triple detergent oil. Right. The 76. It was a sodium, magnesium, calcium blend.
It's a tri-blend, yeah. And the reason why that was developed was for cost, cost performance for API basic oils.
On-road vehicles.
On-road vehicles, not racing. But once you put sodium in, sodium detergents can clean surfaces really well, almost too well. And so
they're very aggressive on the surface.
Very aggressive.
Clean off the surface even of your zinc and your molybdenum additives.
So that's your anti-wear and your friction modifications, especially for cam tappet. So but in 2000, we were already past using of sodium, and we were focused on all calcium because even the mag is okay. It's okay detergent, but for racing, it's not necessary. Basically, the bottom line is after in the discussions with the excellent engineers at Joe Gibbs, we were able to really understand. The key was understanding the system, the engine,
the hardware.
The hardware, the surfaces, kind of surfaces they're using. Is it steel on steel, or is it special dynamite coating on steel, whatever, if it's in the valve train, or we're talking about the piston rings, or what kind of block engine you're using. What's the big difference, and the basic person doesn't know, is that in NASCAR, I mean, the oil is sprayed into the engine, but it's sucked out in very high vacuum, so it's totally different mindset. And plus, you just want the car to go 500 miles. So you want the optimal performance of that oil for 500 miles. You're not trying to do this for 10,000 miles on the road.
Well, I think you make a great point is that on a regular road car, it probably has 5 quarts of oil in we call a wet sump system, where the oil is all at the bottom of the engine and the oil pump picks it up and pushes it through. Right. Where in a NASCAR engine, we had 5 gallons of oil.
Right.
And we had this gigantic wet or dry sump oil pump that was sucking all that oil out. And then basically we're spraying it in the exact location. So we're precision oiling the bottom of the pistons, the cam and tappet interface, the valve springs, because we're using the oil not just as a lubricant, we're also using it as a coolant as well. And like I said, all these different alloys that the NASCAR blocks, later in our time together, they were compacted graphite, which is a little bit different, and how it responded to those detergents and anti-wear additives was different than, say, regular cast iron. There's this guy on YouTube that makes videos that's always saying that application always dictates chemistry. You're going to get tired of me saying that. I got no idea where that came from. But Hambrick says, I'll give you enough rope to hang yourself. But you start off, talk about that relationship and how you developed and what happened going from failures, we're not winning championships. What happened next?
There were a lot of things that happened. A lot of them I don't remember, probably don't want to remember. But one of the issues was they were having a lot of failures breaking in the engines. Yeah. So that was one of the key things they wanted to solve.
If I remember right, it was 1 in 10 camshafts died.
Yeah. So we initially looked at that and tried to help them out with that situation. And we actually developed a, quote, break-in oil specifically for their engines. And the failures pretty much went away.
So explain what a break-in oil is. How is a break-in oil different than, say, a normal passenger car oil?
Well, you don't really need it to go any particular set of miles. You need to break in the camshaft and the lifters and the bearing area, pistons. So you design the oil for those specific needs.
Right. You don't need friction modifiers because you're not trying to make power. You're trying to get those surfaces to mate properly. You don't want too little wear, but you don't want too much wear. You're trying to get just the right amount in a very short amount of time because, I can tell you from the oil analysis side, we see that modern OEM engines can take up to 10,000 miles before they're finally broken in.
Right.
Well, we didn't have 10,000 miles to break in a NASCAR engine.
No, you have
we had about an hour and a half on the dyno.
Number of pulls, and that was it.
It needed to be broken in. Then it needed to race for 500 miles and not be down on power at the end.
Right.
It needed to be as good at the end of the race as it was the beginning of the race.
Right.
So the key thing is when you're trying to flush or spin the system, be if you're going to turn the engine on or even the transmission to spin it. I mean, the key is having a high sulfur oil. So the key is get the sulfur on there. What's that doing? What we're doing is we're trying trying to take from designing the parts. Obviously, you probably have talked about this in your other shows that you're trying to make a smooth enough surface perfectly so we don't have to worry about too much wear. So the sulfur goes on there, takes off the asperities between, when we go into the tribology, the very micron cellulose peaks. Yes, and we remove the top of the peaks, and that's what sulfur does. But you don't want that sulfur there for very long. You want it in and get it out.
Because that sulfur that's softening those peaks, that allows it to be kind of cleaned up, cut off, if you will. If you leave that high level, it basically just continues to eat away.
Yes, it does. And it can cause micro pitting and macro pitting. That's not a good thing.
Yeah, bad.
No, very bad. So the key is get it on there, get it off, flush it. So get all the parts mated well, as you were saying, and get it smooth as possible, and then get it out. So that way we don't have to put much sulfur in the regular oil.
Right.
So that the focus there is all getting is the best friction modification and just enough anti-wear performance to make sure all parts are good. So we solved the cam problem by just putting the right amount of zinc phosphate.
Right type
not
as
too
well.
high, not too high.
Oh, thank you for
and the
mentioning
type.
the
It's
type.
very important. It's very important.
Talk about ZDP types just for a little bit.
I'll let Bill handle it. He's the chemist.
So Mike jokingly calling Bill the chemist is actually referring to this article from the Wall Street Journal back in 2009. They had done a deep dive and found that NASCAR teams were spending millions of dollars developing motor oil to find a competitive advantage. And at Joe Gibbs Racing, we had spent over $10 million during that time working with the folks at Lubrizol to find new technologies that gave us that competitive advantage.
Zinc diphosphate can be made. It has a shrubbery. The alkyl groups on the side of the phos and sulfur. It has. It can be primary or secondary.
Tertiary.
What does that mean?
And not tertiary, but aryl.
Yeah.
What does that mean? Well, it's a breakdown mechanism. So the key is if you are not having, if your system, you need to get it down there fast. You want something that's going to break down there quickly. Early.
Yeah,
And
fast release.
Right. So secondary ZDPs, and we're talking about the alpha carbon that's adjacent to the oxygen, which is then attached to the shrubbery of the phos and sulfur. I know this is too much, but the thing is, the secondary will, under mild stress, will decompose faster than a primary. So the primary is more intermolecular versus the secondary will intramolecular within itself decompose faster. So so the temperature of a secondary ZDP activation is about 110 C, and then I think the primary is about 120 C. But an aero, if you put an aero groups on there, it's going to be 150, 160 C, and that's used completely different for driveline purposes. If you have to have the right secondary ZDP in the right amount, because if you have too much, you may put too much film on there, and then you're going to lose horsepower. So the key is getting the right balance, the right amount. Not too much detergent, not too much dispersant, ZDP, complexation interactions, which may slow down that decomposition process. So that all this plays in the account. So when we were talking with the engineers and how they were spray patterning, the spray patterns were where the oil is going to hit parts of the cam and whatnot. Very important where you channel the oil, and then how much before get it sprayed out. So we try to just get just enough anti-wear protection from the secondary ZDP, just enough dispersant, not too much detergent, and then you bulk up on your friction modification. To the point, yes. So that's the key. And then designing the amount of, as you were talking in other videos, the amount of viscosity modifier is important. Not having too much of that. And the type, yes, as well as having some ester, because synthetic ester can actually help accelerate the ZDP to the surface. So that's very important. But if you have too much, that's going to swamp the whole system. You just have the right amount. And then the type of ester, we did a big study with Joe Gibbs trying to understand the horsepower. So there's certain types of esters that are better than others in terms of horsepower. So you want to get that balance of all that.
Yeah.
Right. So I hope that was not too much there.
Oh no, that's why we have you on here, right? Where else are you going to get this? Nowhere else, right?
But after the development of the break-in oil, then we started focusing on some other aspects. One of them was the assembly grease.
Yeah.
Oh, right.
All right. Greases tend not to have components in them that can clog systems even after you think they're washed off.
Yeah.
So we actually developed a specific assembly grease for racing that was oil soluble, so that once it was put in an engine and the oil was run through the engine, it was completely dissolved and gone.
Yeah.
So it wouldn't cause any problems at a later point. So those two were key in really getting the engines prepared for the racing.
Right.
And then we worked, like Bill said, on the racing oil aspect, and there was a lot of effort put into that.
Yes.
A lot of trials, a lot of dyno tests. I hate to think how much money was spent on that, but there was a lot of money spent and effort was spent.
Millions.
Millions.
Yes,
Probably.
by Joe Gibbs. I mean, Lubricants spent some on them, but they spent a lot of. It was impressive.
What was nice was that Mark Cronquist, who was the head engine guy at Gibbs, he was great that at the end of each season, the last Talladega race, if you will, there was a backup engine for every car. Mm-hmm. So when you had 3 or 4 cars, that means you had 3 or 4 backup engines. Well, that was that year's spec engine. There's no way you're going to Daytona next year with last year's engine.
Right. No.
So those backup engines became donor engines for us to play with, to be able to try different friction modifiers, different base oils, and different viscosity modifiers. That's where we had that freedom to play every year in screen. I mean,
Off season for about a month.
That was the big testing. Test between November and February. So so we get ship. Get the oil shaped for the next season. Yes.
But through all that work that was done, so you had special brake-in oils developed, eventually became part of the Gibbs driven racing oil line, special assembly greases, we had special esters developed for racing. So a lot of the chemistry was, like I said, it was a boutique oil, if you want to call it that,
right, yeah,
for racing.
yeah.
Probably that happened, I would say, around 2000.
It was 2000 when we started. Well,
So, but by the time we got to the point where we were
2005,
really developing.
it took about 3 or 4 years to get really good at. But
by
the oils,
2005.
Bobby Labonte won that 2000 year, the championship.
2001.
First round.
Oil, yeah.
And so, I mean, so Joe Gibbs was all in, and Lubricants was all in trying to do this more. And then we were learning then having qualifying oils as well as racing oils for the qualifying oils.
For the flat tappet.
For the closed
Restrictor
plate for Talladega and Daytona. So so we focused on that too. So they were like 10-weight oils versus.
Oh yeah. Just to put some numbers on it. So like the open race oil, the initial one was around like 12 centistokes. We ended up with the open oil around 7, 8 centistokes. But then the plate stuff, we ended up even lower, 6, 7 centistokes. But then we had stuff for qualifying that was 3.5.
Yeah,
That barely got the engine through the qualifying.
Right,
without damaging anything.
But it made power though.
It did.
Oh, it made a lot of power. Yes. Yeah. So much so that, I mean, like we were talking about off camera, that 2007, 8, 9 in that season. We had 8 or 9 of the top cars. We were working with 3 different racing teams at the time, and that the top 10 was 9 of it were our oils, and so much so that you could tell the story that other racing teams
were trying to bribe us to give them a 5-gallon pail of oil.
Yeah.
Yes.
We'll give you X amount of money for this oil. Or go to the other racing teams. We'll give you so much money for this racing oil. So it was an interesting time back then, seeing how the other teams were responding to what we were doing.
Yeah. Well, because if you compare, say, 2008, that race oil formulation at the time compared to what was on the shelf at the time. So even for, say, a 30 grade oil at the time, right? You're probably going to be somewhere over 2,000 parts per million calcium in the off-the-shelf, API, SM oil back then. Your ZDP was going to be probably a primary ZDP at that time, maybe a blend.
Probably a blend.
A primary, secondary. But it's going to be 800 parts per million. The moly level, MODTC back then would have been 80 to 100 parts per million. Max would have been low. Probably using some type of an OCP, olefin copolymer type viscosity index improver. And it was probably a group 3 base oil.
Yeah, that's right.
If you looked at the same viscosity, Gibbs racing oil, well, the only thing that was going to be common is, you were going to have probably 800 parts per million ZDP, but it wasn't a blend. It was just secondary.
Right, yeah.
You had 1,000 parts per million on the MODTC, the moly. It was a PAO ester base oil with an SBR type viscosity index improver. So nothing about it
Was similar.
was similar, actually.
And that's the point. It shouldn't be similar.
Right.
At that time, yes.
Yeah.
Yeah.
But I think what's interesting is that as you guys learn those lessons early on about the impact of the detergents and the dispersants. Oh, yeah, by the way, the passenger car motor oil back in 2008, how much dispersant would have been in a typical PCMO package back then? What, probably
4%?
4%?
4 to 6, something.
And we had like one.
He didn't need
Right.
it.
You don't need it.
Yeah,
Yeah, for the longevity. Plus, it interferes too much. I mean, the reason why.
Oh, yeah.
It's got to last. I mean, on road, it's got to last for 5,000-10,000 miles. But we're not. Plus, it can disrupt, like I said before, complex too much of the ZDP. We don't use that much ZDP for racing and whatnot.
Yeah.
So that's why we were down there maybe 1.5. I don't know, somewhere in
Pretty
that
low.
ballpark.
Pretty low.
Well, again, that's the point being, don't use race oil in your passenger car.
Not directly, no.
No, it's not made for that. I mean, but if you look at the comparison of what that oil was back then, but now let's compare it to a passenger car motor oil today. We ended up at 0W16 racing at Joe Gibbs before SAE even defined the 016 category, right? We were it was a low 20 back then.
Right.
Now it's a 16 grade. But what I find interesting is when you look at the passenger car motor oil, let's take, for example, the Toyota 0W16. It has 1,000 parts per million MODTC in it. It has 400 or 500 parts per million calcium detergent in it. It's got 600, 800 parts per million ZDP in it. It's going to be a lower viscosity oil. There's probably going to have maybe some PAO in there, possibly some Group 5, maybe some alkylated naphthalene in that to be able to provide that protection. So it's getting in to be a little more exotic. It's not just a regular old base oil. But really the only difference when you look at the additive package from a glance, not the dispersant package, obviously, there's magnesium now. But from a profile point, you can see that there's that racing oil fingerprint
Is evolved
into it, yeah.
Now, obviously, my perspective is the catalyst for that change was low-speed pre-ignition. Once it was found that the detergent package, the type and amount, impacted LSPI, now all of a sudden sodium's gone. No matter how cheap it is and effective, well, sodium was the worst for LSPI, so sodium just vanished from the aftermarket, right? Then you started to see those calcium levels drop from 2,000 parts per million, started dropping down, and now it's pretty common to see them in the 500, 600, 800 parts per million range. Now, that would have been unheard of. I mean, they had more calcium than that in the oils back in the 70s, probably, right?
For sure.
Oh, absolutely.
Yeah. So that's where I see is that the work that was done in racing to help Dale Earnhardt and Bobby Labonte, win championships has actually inadvertently over time, it educated the Lubrizols, the Aftons, the Oranites, the Infiniums. They learned all of these things from racing. And then when the LSPI thing came around, they had the answer. It wasn't like, because at the same time LSPI is coming around, you also we got to go lower fuel economy, right? Yep. We need lower viscosity oils. Yep. We need better friction modifiers because you could throw GMO at an oil and it's going to bring down fuel economy. But what happens to deposits with GMO?
Well, you can get to a problem if you don't have the right system, yes.
So some of the, we'll call it, economically viable opportunities for fuel economy weren't really going to be good for deposits, especially when you're getting in the turbochargers, because now you've got the turbocharger deposit test.
Yes.
So it became more complex. And again, the answer was kind of staring everybody in the face with the racing work that had been done.
Sure. The coatings area started to develop too
Yes.
in the racing business in the 90s and so
Indeed.
forth. And that changed a lot of the aspect on how you needed to formulate the oils to lubricate those coated parts as well.
Especially the friction modification, because the affinity to the surfaces are different than your common cast iron. So that's
Like I said, we went from uncoated parts
Right.
to parts that had, say, titanium nitride or DLC or chromium nitride on it. So now that all those wear contacts in the engine, they're not just metal on metal anymore. It's a coating on metal,
Right.
and that metal surface, that surface texture has now been engineered. It's not accidental. It's not just left over from the machining process. Everything is designed and engineered to work together, and that does change what the chemistry needs to be. Because some of those, we learned this the hard way, some of those additives don't play very well with some of those coatings.
That's true.
very true. It actually etch the surface, which is not a good thing. Or they don't even react at all to the surface, and then you got all kinds of different situations. So,
And now we're seeing those same coatings making their way into modern production engines.
Correct.
It's not just for racing anymore. I mean, something like DLC was not common in production engines, but now it's
and not easy to replicate either, because there are a lot of places where it had real
Difficulty
difficulty
depositing.
giving a consistent film or consistent DLC over or whatever coating you want to put on there. They were struggled. There was very few good houses that could do that.
yeah.
That was a problem. But now it's, I mean, the advancement of that is just incredible. So, in the material science, and Doug James could talk about a lot of that if he was here.
Just fun little stat. Prior to Joe Gibbs Racing working with Lubrizol in the Fab Five, they had won a total of 0 championships, and I think it was around like 16, 17 races. It was less than 20 races. That was the 8 years prior. In the 8 years following, they won 5 championships and over 80 races. Putting the science of tribology and those custom designed fluids into the race car made that big of a difference.
But we have to thank Joe Gibbs too, because I mean their openness to work with
to
us
change things.
and our management to allow us to do that. So we were able to put all the minds together and try to understand the whole system, and that's what you've been talking about. The details of this system it's phenomenal.
And for a short period of time, Lubrizol actually had a racing consulting services business.
Yeah, the championships that the Lubrizol technology won for racing wasn't limited to just Joe Gibbs Racing. It went into many different aspects of motorsports.
Yeah,
NHRA Pro Stock. Yeah,
I don't know how many championships we had won in the drag racing side.
KB Racing run 8 straight with that oily design.
Yeah,
It was an offshoot of Joe Gibbs.
but I would say, because of Gibbs calling into Lubrizol,
Yes.
all of this happened. If that hadn't happened,
Yeah, we didn't get the call.
or if my boss said, "No, we're not doing that,"
Yeah, none of this would have
and I
happened.
still have my neck. There's no rope around it.
Yes. He's retired well, and so am I.
He's retired, not fired.
We're retired.
Yeah.
But it's a big difference. That's good.
But that team that we put together at Lubrizol was just a fantastic team. Bill Abraham was obviously on the chemistry side. Myself, sort of on the testing and management side of things.
Doug Jane with
Doug Jane, our super guy with
the
surface
tribology.
analysis, and
So, I mean,
tribology, coatings analysis.
he worked at NASA, and he's a surface expert.
Yeah, and John
Material
Martin, who was our motorhead, I'll call him.
Yeah, well, he's experienced in racing.
Yeah,
so,
he has experience in racing.
And
too, so.
then Sarah Kipp helped as well as later in the team.
Yeah,
She did a great job.
Sarah put up with all my BS,
Yes.
right? Because I was always wanting to iterate, and so she was the one doing all the rest of the work. I have this idea. Can you finagle that?
Work with the guys to get this done.
Make that done. And she made it happen. She was awesome.
She's a doer. She's very good.
Yeah.
She's
So
very
that
good.
team was amazing. I mean, I don't
Yes.
know that we could have pulled together a better
No,
team.
that was a match made in heaven. It really was.
Well, and I said the learning that came from that was amazing, not only just for you guys personally, but for the company, but also for me. This is, like I said,
While you're here.
this is why I'm here. I learned this stuff from these guys. And
You learned it well.
and what's awesome is that because of this incredible platform called YouTube, we're actually able to share this kind of information with you. And hopefully this is valuable to you. If you do find this valuable, make sure you hit that subscribe button and share it with the other motorhead friends, because there's more to come in the future from me, the Motor World Geek, and maybe we'll get these guys back some other time. Thanks for watching this one. We'll see you next time.